Hi everybody. So I was asked to do this problem. It's problem 23 from chapter 14. It says a 200 gram mass is attached to a horizontal spring, oscillates at a frequency of 2 hertz. There you go. At one instant the mass is at x equals 5 centimeters and has a velocity of negative 30 centimeters per second. Determine the period, the amplitude, the maximum speed, and the total energy. So let's do it. For part 1, it says determine the period. Well, good news is I got the frequency, and the period of anything is just the inverse of the frequency. So that means it's going to be 1 divided by 0.5, because 2 hertz. Getting ahead of myself. 2 hertz. So that's going to be 0.5 seconds. So 0.5 seconds is the period. Alright, there you go. For part B, let's see here. We got what is the amplitude? So, often when I see amplitude and I'm trying to solve one of these problems, I think of things like the conservation of energy, because I use the conservation of energy at the amplitude, the maximum displacement from equilibrium. That's where I have the most potential energy. So I often think about the conservation of energy. So let's see if we can use the conservation of energy to solve this. So if I got this spring mass system, I got it like this. So let's say here it is at its equilibrium position. So this is when it's at its equilibrium position 0. Let's say then this is, so let's say this is the amplitude, the maximum amplitude here. So here's the amplitude, that's the maximum, the maximum displacement. So the amplitude would be the maximum displacement. And then at some random point, let's say here, I don't know exactly where, let's say here, that's where the displacement is, where they say is 5 centimeters. So here is 5 centimeters, 0.05 meters. And then we also know that the speed is moving back this way. So that's the velocity at that point, which is negative 0.3 meters per second, or 30 centimeters per second. Okay, so I'm going to say this here is my, let's say final moment. This is my final moment. And then here, where it's at its maximum displacement, that's my initial moment. So if I do that, I'm going to use the conservation of energy. So my initial energy is equal to my final energy. My initial energy here is at its maximum displacement, so it's going to be spring potential energy. And then here I have both spring potential energy because it's displaced from the equilibrium position, but I am also going to have kinetic energy because it's moving. So I'm going to have spring potential energy at the end plus the kinetic energy at the end as well. So it's going to be 1/2 K A squared, that's the maximum displacement, which is going to equal 1/2 K, I'll say X final squared, plus 1/2 M V final squared. So that's the Vx right there. Something good that happens is all the 1/2s cancel out, so that's nice. And then lastly, I'm going to isolate A here. So divide everything by K. And this K cancels, and I got M over K times V final. So I have A squared equals my final position squared plus M over K, and then V final squared. So lastly, I'll just take the square root of all this, and now I just got to plug everything in. So V final squared plus M over K, and then X final squared, and then this is V final squared. Alright, so kind of off to the side now here, I'm going to write in things that I know. So I know my X final is 0.05 meters. I know my final velocity is 30 centimeters per second. That's 0.3 meters per second, and I know my mass is, I think it's 200 grams, which is 0.2 kilograms. And yeah, so there I go. And so you might think, great, I know this, and I know this. So I can solve, oh, darn, but I don't know what K is. So I need to find the spring constant, and once I can do that, I can solve this thing. So to find the spring constant, I'm going to use my period equation. It's 2 pi times the square root of m over k. So we got that in our lab the other day, that the period of a spring is equal to 2 pi times the square root of the mass divided by the spring constant. Let's see, divide both sides by 2 pi. That'll give me this, and if I square both sides, that'll give me m over k. So then isolating k, let's see, if I multiply both sides by k, that'll cancel that. And then I get k is equal to m divided by, if I divide by all this, that's going to be the period divided by 2 pi and all of that squared. So if I look at that, the spring constant then is the mass, 0.2, divided by the period, which is 0.5 that I found before, divided by 2 pi, and then I'm going to square all that. So my spring constant is, let's see, so 0.5 divided by 2 pi, that's about 0.079, so about 0.8, but I'm going to square it. It's about 0.00633. And then I do 0.2 divided by all that, and I get about 31.6. So 31.6 newtons per meter is my spring constant. I'm going to plug that in there. So let's see, hopefully if I plug all this in now, I'll be able to get my amplitude. So it's going to be the square root of my final position, which is 0.05 squared, plus my mass, which is 0.2, divided by my constant that I just found, which was 31.6, and all that multiplied by the speed, which is 0.3, or negative 0.3 technically. Should be negative 0.3. But it doesn't really matter because all this is being squared. And then take the square root of all that. Let's see. So I get 0.3 squared times 0.2 divided by 31.6. Okay, I'm getting about 0.000566962 plus 0.05 squared. And then I take the square root, and I get about 5.54 centimeters, or 0.0554 meters. So I can get about 0.0554 meters, or I could basically convert that to 5.54 centimeters. Either way works. Centimeters, there we go. Both of those are legit. All right. So moving on to part C. Part C says, what is the maximum speed? So again, I think I'm going to use the conservation of energy with, except I'm going to change my final moment to here instead of where it was before. So, because here, at this point, I know that I have just kinetic energy. Where here at my initial moment I have just potential energy. And I can use that, and again, the conservation of energy to solve this. So I'm going to say, all right, my initial energy is going to equal my final energy. My initial energy was spring potential energy. My final energy is kinetic energy. All right, so 1/2 K times the maximum displacement, which is the amplitude squared, and then equals 1/2 mv, and that's going to be my final velocity, which is the maximum velocity at the equilibrium position squared. The 1/2 cancels out. Now I'm just going to isolate for velocity. So divide both sides by m. I'm going to have k over m. A squared is v final squared. Take the square root of both sides. It's going to give me the square root of k over m. Multiply by a squared. That's going to give me the final velocity. So it's the square root of k, which is 31.6, divided by my mass, which is 0.2, multiplied by my amplitude, which I found to be 0.0554, squared. Taking the square root of all that. Okay, let's plug that in the calculator. And then square root all that, and I get about 0.7. So my final velocity is 0.7 meters per second. And there you go here. That's what I think is going to be the maximum velocity. And then lastly, let's do part D. Part D says total energy. So total energy of the system. Well, total energy is really any one of, so I can highlight any one of these parts. So it could be this initial moment. If I find the where the total energy in this case has all been converted into spring potential energy, that'd be the total energy. I could add up both the kinetic energies and potential energies of that moment, and that would give me the total energy as well. Or all the total energy gets converted into kinetic energy here. I could calculate that and find out the kinetic energy. So really any one of those situations will work. There you go. I got the velocity right there. So might as well just use the kinetic energy. So the total energy is the maximum kinetic energy. So that would just be 1/2 mv max squared. So essentially then the total energy would be 1/2 times the mass, which is 0.2, times the maximum velocity, which is 0.7 squared. Plug all this in, 0.7 squared multiplied by 0.2 times 0.5, and I get 0.049. Joules. And there you go. There's my total energy. All right. Hope that helped. See ya. Bye.